Do we need this reversing? Excuse me, do we reverse this as well? Do we reverse this?
Yes, we should. Well,
Yeah. That's to see you, I mean. Well, he's sharing his screen. That's his screen.
Oh, that's all right then.
Yeah, but that's just so he can see you. Okay?
Yeah.
Okay, it's my pleasure to introduce the next speaker, who's Albrecht Giese, who's going to talk about the Sagnac effect disproves Einstein's relativity. Okay, over to you, Albrecht.
Yeah, hello and greetings, hello you all. Yeah, well, about the Sagnac effect. And the Sagnac effect is presently an important one to my feeling. And why is this Sagnac experiment important? This experiment answers the question of the constancy of the speed of light in an arbitrary frame of reference. And so it decides between the relativity of Einstein and the relativity according to Lorentz. So we have to talk, I will talk a little bit first about this relativity question. We have two ways of relativity. The one of Einstein, which is based on principles. And the principle of relativity is the following. The laws of physics are the same in every inertial frame. That is Einstein. And he has based his relativity on this. We will see it later a bit more. The second way is of Lorentz, and Lorentz has based relativity on known physical processes. These are two processes in general, are in principle for special relativity. Temporal processes slow down at motion and fields contract at motion. Lorentz way gives the same results as Einstein, but the mathematics is dramatically simpler. Also, imagination is much simpler with Lorentz than with Einstein. And this way resolves, in addition, unresolved problems like the dark matter and dark energy problem, also inflation and things like that. Okay, we start with special relativity as 3 points: contraction, dilation, the constant speed of light, constancy of the speed of light. And piece by piece, the contraction, Einstein has defined that space must contract so as to fulfill the relativity principle, which was his guiding way. For Lorentz, it's a contraction of fields, and that is a physical fact known from the Maxwell theory found by Heaviside. And so it is a physical fact. And here the equations here, you know that it's found again in the Lorentz transformation later. And Lorentz was able to fully explain the Michelson-Morley experiment, since the Michelson-Morley experiment contracts also at motion, which explains not fully explains the null result of the experiment. So dilation of time, again, Einstein has to define the dilation of time so as to fulfill the relativity principle. For Lorentz, this is not about time, but more physical, about oscillations. And there are internal oscillations going on with speed of light in a particle. That was a physical fact which was suspected around the year 1900, was a bit speculative at that time, and later confirmed 1930 for Dirac and Schrödinger. So if you, precisely speaking, it's done for the electron, but there's no reason that other fermions do it in a different way. And this dilation propagates to all oscillations and also in our macro world. You can see it here as a principle here. If you have a Dirac light clock and you move it and you see the period, the time of a period is extended, and this causes this equation, which we know. And if we assume a particle model, which I assume with subparticles orbiting at speed of light, it's also the same cause for dilation. So there, now back to Sagnac. There are two opinions about the Sagnac experiment. The one say the Sagnac experiment conforms to Einstein, and this was frequently investigated and published, and most with this result. And also the Sagnac experiment conflicts with Einstein. Who is right? One can say both are right in a different way or for a different perspective. This positive opinion is correct for an observer at rest who checks the setup of from the outside. The Sagnac setup looks from above to the thing and looks what happens there. That is all in confirmation, conforms to Einstein. And the other one, it is that it not fits, is correct for an observer who moves with the system, which is particularly actual for navigation systems. I had to do with such navigation systems, and so I was brought to use this again as an argument pro or contra the conformity to Einstein. This is the Sagnac in a simple way, this Sagnac setup. We have a light source here, and the light goes through a beam splitter. One part goes straight to a mirror, and then to a mirror again, to a mirror again, and then again straight to a detector. And the other one is reflected here, goes this way, mirror, 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 and back also, and comes to the detector. Of course, only a part of it, but there comes something. And here we can have interference relation, and this interference is in a stable situation, a constant picture. So now, that's the interesting thing. If we rotate the whole apparatus, then it's easy to say that now the way here going with the rotation is a longer one. So it needs, the signal needs more time to arrive here at the detector. And the other one, opposite to the motion, needs a curve, shorter time, and comes here on. And so this rotation is indicated by a change of this interference picture here. Okay. And in this view, if you look into it in this way, it is no problem with Einstein because every motion here, every part conforms with Einstein. That is a view from an observer at rest. So, and this is used, for instance, here, what I've seen as a technical realization. Here, it's not mirrors, but we use a fiber optic here and use several wines. The more, the preciser is the whole thing, and it happens, it's going on the same. Here, the light beam goes through the beam divider this way and arrives here to the detector, and the other one is reflected here, also goes the other way around, and also ends up with the detector. And that is, again, very sensitive to a rotation of the whole apparatus, and can be used to measure or to detect rotations, which is very essential for navigation systems. We had earlier, you know, perhaps mechanical gyroscope platforms used in planes and ships. They are very heavy, very expensive, very need very much maintenance and so on. This is a very simple device. You can see this is, for instance, such a box you can buy, which has it in it. And the precision is, I think, great. It can have 1/3 of a degree deviation or precision of a day. So if it's more than 1/10 of a degree per day, this will be detected by such a device. Okay. Yeah, and my statement, this navigation function only works because Einstein is wrong, and I want to show you that. So here we have now one of the wines, yeah, it's good enough to explain it. It's not so precise, but you can see in principle how it works. There's again a light source which feeds in light. Can be a wave again, but we can also take a pulse, which is more practical because then we can measure with a clock how much time such a pulse needs. So this light pulse goes, what does my cursor do here? Goes this way. I've colored it green to distinguish it from the other one here around. And at the same time, of course, this is the other going the other way also by a beam splitter, and they meet here, and if they are waves, they make an interference section, or we can do it in the other way, that we take pulses and can measure the time which is needed here. And here this is the equation, the time right hand and left hand is the same, and the speed of this pulse is the circumference divided by the time which is measured. Now, if it's now rotated the whole thing, then the meeting point during such a way, one circuit goes here to this side. So one way again is longer for a pulse, and for the other pulse it is shorter. For the green pulse it's shorter. That is indicated here. The one is shorter. That is one which goes opposite to the rotation, and the one next is longer time, which can be measured here. And so we measure a speed, or calculate the speed from it. And for the brown circuit or pulse, the speed in this system, in this rotating system, is c minus v. V is the speed on the surface of this apparatus, and the speed, green speed, is c plus v, also for the observer of the system, more than the standard speed of light. So we look at more careful to this whole thing, because that is an essential part of this consideration. We take a little sector out of it and look further to the sector, that is this one. And this is only now the brown pulse. That is sufficient to look at one of them. And of course, the speed which I've shown on the previous one is the same all over this whole circuit, because that is given by symmetry. So, and this now moves into this direction on a circuit, and for observer, that should be observer, which moves with the whole thing here, this rotational motion. For him, if he measures speed of the pulse, it is c, speed of light, minus v, which is the speed of this thing. Okay. Now, it is not the speed of light. So one could say in conflict with Einstein, but special relativity is not for rotational motion or for curved paths. So it's not by itself, this is not a real information about it. But to get this, we take here a little straight piece of such fiber optical piece. And here a pulse moves also to this direction, and the whole thing here, the whole piece of fiber moves in the same direction tangentially with the same speed. And if we now measure the speed of this signal here, we get, of course, can we expect the speed of light, the nominal speed of light. Okay, now we have here different cases with different measurements. Yeah, but we can now consider the following. We have here this difference, and we have this number here, this value here, and this difference between both is v, is independent of the radius here of this circuit, of this loop. So we can increase this radius, and this will not change the difference. We can increase this as much as we want and can. The difference always is v. So now we can increase the radius until it reaches infinity. And if it reaches infinity, then these two sections here and here become physically identical. But still, we have the case that here we have c minus v and here c. So, and then we have a conflict, because in that case where they are when they are physically identical, they should have the same value. Who is right now? Which one is right now? This is right correct, because it is a direct measurement with one clock at the end. And why is this different? And that is now the interesting case. It is different. We have to use two clocks here to measure this one-way. For a one-way piece, we always need two clocks. And these clocks, of course, have to be synchronized. And the problem is, how are they synchronized? So again, the difference between both measurements is independent of the radius. And we have here made the transition from the Sagnac case, which is here curved, to the Einstein case where it is straight. Yeah. Here now, Einstein synchronization, that is a problem. This is facsimile of his famous paper of 1905, where he explains in German what how synchronization is done. I have taken it out here again in German, and here I have the translation to English. Okay, and Einstein says to synchronization to this topic, but it is not possible without further definition to compare an event in A, one position, and an event in B, the other position. We have defined so far only an A time for the event in A and a B time for the event in B, but no time common for A and B. The latter time for both can be defined by stating by definition that the time which the light needs to get from A to B is the same as the time which it needs to get from B to A. Okay, and we assume, says Einstein, that this definition of synchronism is possible in a contradiction-free way. And here we have to contradict Einstein. It is a contradiction here in the case of Sagnac. Again, what Einstein does, just to make it clear, we have two clocks which have to be synchronized. The whole thing is moving, and we send a signal from A to B and a signal from B to A. And Einstein says we rely on the fact that T1 and T2 are both the same. So, and this assumption of Einstein is only correct if C is constant in any moving system. And that now is circular reasoning. If you synchronize two clocks in this way, then you can measure any speed of light and you will always get the same value. It's a circular reasoning. Yeah. So if clocks are synchronized in this way, the speed result must always be speed of light, the nominal. So, and that means, or the result is, the conclusion is, the constancy of C is not a property of nature, but it's a property of Einstein synchronization. I hope this is understandable. This is the essential result of this view on the Sagnac experiment. So we have the other case, which we know that is a two-way measurement. Light signal is sent to a mirror and comes back. And we measure this nominal speed of light. And if this is moved, we measure the same speed of light. But we know if this is moved, the clock will run with a different speed. And also these distance, the mirror will, by contraction, move closer to these points here of the sending and receiving point. And that is, of course, given, and that is given, as I said, already by the Maxwell model. So here's the other point, 2 points. The clock runs more slowly in motion, and the distance d contracts in motion according to Maxwell. And this also covers the Michael-Morley experiment, because that is what essentially goes on by the Michael-Morley experiment. Okay, so with this result of Sagnac, the Lorentz version of the relativity is the only surviving one. And this has tremendous consequences. We do not need any four-dimensional space-time in special relativity. We do not need curved four-dimensional space-time in general relativity. We can use Euclidean geometry, and that is dramatically easier mathematics. So because, why did Einstein do it this way? To show it in a simple way, he had to solve this equation: c plus some speed v is against c for any v. And this is not possible by Euclidean geometry. So Einstein had to invent a new geometry that was space-time, what he has invented to solve this problem. And for special relativity, this is the Minkowski method. And for general relativity, it's the Riemannian geometry. This space-time is a cause, as we know, if we have learned it, for many problems and for the difficult understanding of Einstein's theory. And when we do it with Lorentz, we can add it in the normal way, Euclidean way. Of course, now we have to take into account that these single speeds are normally measured in a different frame than the result of the sum. And we have then, of course, make a transformation to the frame of the observer. And then we get as a result, again, as a nominal result, the speed of light. But that is a consequence of this necessary transformation. So the consequence of Euclidean geometry. Again, what is the relativity of Lorentz and the solution of Lorentz? It is based on a variable speed of light, which has a classical summation, and an absolute system, which is sometimes called ether, but that's a bad word because we associate ether with something which is no more physical. But the whole thing is based on physical phenomena. That is a special thing of Lorentz. So, and we also can go to a general relativity. The Lorentzian, there's also a Lorentzian way of general relativity. And well, it is very simple. It needs the following elements only. It needs the C oscillation with C in elementary particles, which we have already used for special relativity. And it needs the reduction of speed of light in a gravitational field. And this is something which was almost found also by Einstein. He has written a paper in the year 1911, where he has taken this phenomenon to draw conclusions out of it. But he made in his calculation an error. He had an error. And so he didn't continue. He should have continued. Then he would have, I think, ended at the same thing as I'm showing it here to you. So now we have here with general relativity a much simpler mathematics. Do not need curved spacetime. And I will show you this at an example. And this is the deduction of the Schwarzschild solution. I think you know the Schwarzschild solution, but I can say it again. Einstein's field equations are very complicated, and Schwarzschild has built a subset or reduction of it for the case of spherically symmetric field, like around the sun, and then anything becomes much easier, much simpler. And this is the case which is often happens and is often the case in questions of astronomy, and so it's helpful. Okay, here is the deduction of Schwarzschild solution. According to Einstein, these are more than 80 equations. I've copied them from a textbook about general relativity. Without text, just equations one after the other. And to understand these equations, we have to understand Riemannian geometry of the four-dimensional curved spacetime. And here, Einstein's field equations, which is also quite complicated. Not every physicist is able to do it, but if one does it, and does it correctly, then it ends up with this version, for instance, of the Schwarzschild solution. That is with Einstein. And now I show you how it works with Lorentz. We start here with the part of the Lorentz transformation, which describes the time dilation. A special way to write it down. And we could deduce it here again, but it's so simple that I take it here as it is. And we make a little transformation. We split it up to polar coordinates because it is needed later. And this is still without gravity. That is in a gravity field situation, gravity-free situation. Now we switch on gravity and we get these changes. The speed of light changes is reduced in a gravitational field in different ways. It will be different for radial motion and for tangential motion. And because this is different, also fields which are described by exchange particles which move at the speed of light, we get a contraction in the radial direction. That is just a consequence of these two facts. Okay, and this is inserted here now, piece by piece, and we get these changes in these parts here. Okay, was not so difficult. We have only to fill it in here. And now we reorder it And what do we get here? The Schwarzschild solution. And look how simple it was. You can do it at school. The other thing you cannot do in school. To compare it again to Einstein, this is Einstein, according to Einstein. I'm sometimes, if I discuss with other physicists what is better, Einstein or Lorentz, professors normally tell me Einstein is so much better because it is so much simpler than Lorentz. Yeah, this is the simplicity and the simple way of Einstein, and this is the complicated way of Lorentz. You can make yourself an opinion what you think, what is better, what is the correct version. Okay. Can we say again to this? Oh. No, okay, there are many other things. I have investigated other situations of general relativity, and I also found one can do them with Lorentz, and it's simpler and it has the same result. Okay, we may come back to this again. Okay, so what is our lesson? What is the conclusion from these things which I've shown you? Einstein's assumption of the constant speed of light in any frame is a historical error. He does it with his way of synchronization, one could say. And that is circular reasoning. Einstein's assumption of the absolute absence of an absolute rest frame is also a historical error, which both hang together, logically are connected. The corresponding change towards the Lorentzian relativity is a return to physics. It facilitates the mathematics used in a much simpler one, and it solves open problems like dark energy, dark matter, inflation, and so on. So here another summary from Christoph, philosopher Hans Reichenbach, German philosopher. He has cooperated several times with Einstein and has written some books about relativity. And he has made the following analogy. He said, we can see Einstein's relativity analog to the Ptolemaic system and Lorentz's relativity analog to the Copernican system. And that is also what I feel. I think this is a good description of the situation. So in general, the change towards is another summary. The change towards the relativity according to Lorentz is a return to physics. It simplifies the mathematics towards a much simpler one while keeping the core results according to Einstein and solves open problems, as I've said already. So now a question to you who are listening to my talk. If somebody of you in the audience doubts this fact, and this fact is the fact that Einstein and Lorentz has the same results than Einstein, please name me a physical process that you think can only be processed via Einstein. And I think I can answer to it, and I'm quite confident that I can show you that it really works. So why, a bit history now, philosophically more, why did Einstein follow this way? Lorentz, when he made the beginnings of relativity, has used physical facts which were speculative at his time, however ensure today, like the internal rotation with speed of light. Einstein was subject to the zeitgeist, mainly for the positivism, that is a special understanding of what reality is, which was also taken in the same way by Heisenberg. Einstein has attended in Germany the German Humanistic Grammar School. And this grammar school, I know it by my own experience, follows the philosopher Plato in the way that for Plato are structures and principles the basics of our world. And Plato says matter, or material, how shall I call it? Matter is a kind of a delusion. It means nothing. It means nothing. That was Plato's opinion, but what builds our world are structures described by principles. Okay, that's what I wanted to tell you, and I thank you for your attention. Sorry. Yeah.
Can I take questions from Zoom first? How do I do that?
Yeah.
Yeah, can I take questions from Zoom? John, you've got a question.
Yeah, and you have to make active your, yeah, okay.
I was applauding.
Oh, anybody got a question on Zoom? John, you've got a question. John, have you got a question? No? So have we got questions from the audience?
Yes.
From the live audience? Roger, have you got anything to say?
Hello. Yeah. Can you hear me?
Yeah, we can hear you.
Yeah, it's about the synchronization. What I've read that is the only way you can do a synchronization is by Einstein's synchronization, and any other synchronization leads to the same thing as Einstein's synchronization. Is that correct?
You say Einstein is equal to Einstein, or what is it? What do you say? I'm not sure.
But it's about the synchronization.
Yes.
You've got Einstein's synchronization,
Yeah.
and any other attempt to do synchronization a different way still ends up with the same result as Einstein's synchronization. Is that correct?
I do not know any type of synchronization which is similar to Einstein's. Yeah, you can synchronize clocks in a simple way if you assume a certain frame of reference. I've written, and that is a consequence of Lorentz, that there is an absolute reference frame in our world. The problem is, because we have these relativistic effects, that we have no way to, up to now, to find where, or that means in which motion state, this frame of reference is. But as long as it is this way, then we can say we define our frame, or whatever it is, some arbitrary frame, to the absolute frame of reference, and can refer all physics, what we are doing, to this frame. And then synchronization is a simple case. You have two clocks, you take one clock to the other clock and look at that they have the same indication, and then you can take them apart slowly. Yeah, but there's no other thing happening.
I think that's slow clock synchronization, and what people have said to me is that gives the same result as Einstein's synchronization.
You know, if you take the general case of Einstein and you have your frame of reference where you do your experiment, your measurement, then you have to assume, according to Einstein, that the whole thing which you think is system at rest is in fact moving. And if you now take a clock to the other, one clock to the other one for synchronization and take it back, then there is in the moment unknown way in which now the both clocks change their indication, they run in their indication. So it's not trivial then to do this. It is trivial if you assume that our system is a system at rest. But for the case in motion, you need something. But Einstein's method does not work, as I've shown. We do not have any other things. The only thing we can do is that we define something for the moment as a system at rest, make our measurements there. And if we go then to another system, we know how we have to transform time from our this system to the other one. That's the only thing we can do.
Okay, thank you.
So do you think we have an absolute frame of reference now? For example, the background radiation, or maybe the Higgs field. Albrecht, you think?
We could sometimes said also, and I think that's reasonable, that we take the background, the microwave background, as our absolute reference system. It's not, I think, not very precise, but it is a way to do it. And if we do it that way, we will have no problems to calculate with relativity, to work with relativity. It's a good point. I would say the absolute reference is the point where, or the motion state where the Big Bang has happened. But how can we find where the Big Bang, or in which motion state the Big Bang was? Okay, the only thing we have to have reference to that is the background, the microwave background. When we say from the Big Bang to the microwave, the maximum speed was the same to all directions. It's an assumption, but maybe it's a reasonable assumption.
Any questions, any further questions from the live audience? And any from Zoom? Any statements or questions? Okay, well, what we'll do now is take a short break till we have the next speaker. And I will just mention that at the end of this, John Torday is going to speak next. At the end of that session, Mike wants to do some sort of, I don't know whether are you saying anything, Andrew? No, you won't. So Mike Horner wants to conduct some sort of discussion for about 10 minutes on using Zoom and so on at the end of the session. But at the moment, we've got a break now to relax for a bit, and then we've got John Torday to give the last speech. Okay, let's thank Albrecht again.
Thank you.
Thank
you. Thank you.
Thank you.
So we should stop the recording. Yeah, stop the recording.
You gonna do it?
How do I do that? Stop the recording.
Look at the bottom row.